so we'll get started. So I'll give an overview of three, okay, maybe I'll just go to the next slide. So yesterday we talked about kind of what are some of the explanations for earthquake hazard in central and eastern Canada and how we try to incorporate some of this information into our seismic hazard model. Today we're going to talk a little bit about what are some of the elements of a probabilistic seismic hazard assessment or analysis. What does the 2015 fifth generation model look like? So that's the model you guys have on your computers and the model that's being included in the new risk assessment model that Marie and his team have been working on. And then I'll conclude with some of the updates we've done on the model as proposed for the 2020 edition of the building code. And most of the talk will be kind of Eastern Canada focused. And I'd also encourage if people have questions to just ask them kind of as they come up. Okay, so we do seismic hazard analysis because we spend a whole great amount of effort in Canada for recording and monitoring earthquakes. But if we want to do something with that data, it's not super quantitative to know, okay, well, we have earthquakes here, but what does that mean? When we're trying to create earthquake-resistant structures, we'd like some sort of quantitative measure of what the hazard is at the site. And so that's really when seismic hazard analysis comes in, to transform an earthquake catalog into something quantitative. So when we talk about probabilistic seismic hazard analysis, what we're trying to do is estimate the likelihood of ground motions that may be exceeded in a given future time period at a particular location. And we try to consider all possible earthquake scenarios and their probabilities. And this is why we call it a probabilistic assessment, because we consider all scenarios and their uncertainties. And at the end, what you're trying to do is calculate a probability of exceeding ground shaking. So an example of that would be there at the bottom. 2% in 50-year chance to exceed a PGA of 1G would be the result of a probabilistic hazard analysis. But we always calculate for one or the other. So we can calculate for probability. So we can calculate what is the probability of exceeding 1G ground motion. Or we can calculate at a constant probability, such as 2% in 50-year, what is the ground motion that we can expect. And this is often what we do because we'd like to have a uniform level of probability across Canada so that earthquake-resistant engineering is kind of equitably distributed across the country. And just so we're all on the same page, when I say 1G, it's 1 unit of acceleration, so 9.8 meters per second squared. And we use acceleration because oftentimes this is what the engineering community asked for in order to be able to kind of create earthquake-resistant engineering. So we either solve for probability or we solve for ground shaking. So these are kind of the very broad parts of a probabilistic seismic hazard analysis. So one of them is determining earthquake history. And so this is where do earthquakes happen and how often do they occur. And then the second part is, given these earthquakes, how strong is the shaking from them? And this is what we call ground motion models or ground motion prediction equations or attenuation relations. They have a lot of names, but they're all basically the same. So earthquake history, by that I mean an earthquake catalog. So in Canada, we record earthquakes. We have a seismograph network across the entire country, and we're constantly monitoring and recording earthquakes. And there's also paleoseismology work to kind of look at historic records and how big were they. And when you're looking at this, you really need to consider how complete is your catalog. Is it complete to a magnitude 1, a magnitude 2, or magnitude 3? What kind of magnitude types you use. Not all magnitude types are created equal. And then you also have to consider, are you going to be looking at just natural seismicity or induced seismicity? And you might want to treat those differently. So I introduced this a little bit yesterday. Next, we have to kind of determine what are the spatial extents of the seismicity. And we try to group like seismicity together because they have either maybe they might be on the same feature or they have a common recurrence. They might be on the same fault. And you can do this in different ways. You can do them with areal polygons, and that's a lot of the stuff that I showed yesterday. And this is just a map across Canada showing all of the sources, areal sources that we have. You can also have fault models. And so we have this in Canada, for example, for the Cascadia subduction zone. We have that as a fault. It's a relatively well-known fault that we have a high confidence of its geometry. And another type of model that we don't do in Canada, but is very common south of the border in the United States, is smooth seismicity. And the next thing we will have to calculate is the rates. And that, what I mean is how often do earthquakes occur in all of these individual boxes. And there's different ways of doing this, like I showed yesterday. So here's just a zoom on Eastern Canada, and we touched on this yesterday. We have a historical model, we have a regional model, and we have a hybrid model. And then we calculate the earthquake statistics within each of one of these source zones. So here's again an example from the Gatineau seismic zone. So this is in the West Quebec seismic zone. And you can see that we fit a cumulative earthquake recurrence curve. And I'll talk a little bit about these as we progress when I talk about the 5th generation model of how we actually come up with these. So the next step is we have to kind of characterize, given a certain earthquake of a magnitude, and you're a particular distance from it, how strong is the shaking from that? And you have to make sure that your ground motion models are appropriate for your region. And I'll just briefly go over some of the parameters that change how ground motion models look. So no surprise, they're a function of magnitude. So I'm going to have a lot of plots that look like this. So on the left scale, it's a measure of the amplitude of shaking, in this case, the pseudospectral acceleration at a particular period. And on the bottom axis is distance, so how far away you are from that earthquake. And this is just an example of a NGA West 2 ground motion. So this is the type of ground motion relation we use in Western Canada for crustal events. And you can see as I increase the magnitude, the strength of ground motion increases. 10 to 0 here, that's 1 G. This would be 10% G, this would be 1% G. So, yeah. SA means it's a spectral acceleration at 0.2. And I'll have about 6 slides. I'll just explain what that is. I mentioned it's a function of tectonic environment. So here's an example of 2 different ground motion models, one that's appropriate for Eastern Canada and one that's appropriate for Western Canada. So when you're kind of selecting these, you have to make sure that the ground motion model is appropriate for your region. And this largely comes back from a geology standpoint. The geologies are different, so the propagations of seismic waves are different. You can see that, for instance, at a distance of about 100 kilometers, if you were using a Western ground motion model, you would underpredict the amount of ground motion because the attenuation with distance in Eastern Canada is much more gradual, it's much slower. It's also a function of period, and that's kind of alluding to that. So whether you're looking at shaking at a short period like 0.2 seconds or 2 seconds, the amount of shaking is different. And this is important from an engineering standpoint, because when we calculate hazard, we calculate at spectral accelerations. This is how a single degree of freedom damped oscillator, which is kind of a very, very simplified building, would react to shaking. And it has a certain resonant frequency. So it might be at 2 seconds, 0.2 seconds. And engineers use these kind of simplified models to figure out how their building will respond. And so a short period measurement is appropriate for a small building, whereas a long period is more appropriate for a tall building. So 2 seconds might be for a 20-story building. The other thing that's really important in a probabilistic seismic hazard analysis is understanding your uncertainty. And this is why we call it probabilistic in a lot of ways, is because we're trying to quantify all the different types of models that we have. So one form of uncertainty is we call aleatory. And this is basically saying that earthquakes are inherently random. If I'm 10 kilometers from a magnitude 6, and I'm in a completely different place, 10 kilometers from a magnitude 6, I'm not going to have the exact same ground motion because there are a lot of random processes going on. And that means there's some deviations in what the ground motions may be. The other form of uncertainty we talk about is epistemic. And this is basically under the notion that we don't have enough data and we don't have enough information, so there are a lot of different models that might be correct, and we don't know. And so we have to model different alternatives to kind of sample what we think we know. So here's an example of the way you handle aleatory uncertainty in ground motion models. So this dark or solid line is the median relationship, and then you have a standard deviation around that. So you might have +1 standard deviation, -1 standard deviation ground motion. And it's a bit easier if you think about this kind of figure to the right. So these circles are a bunch of ground motion recordings. People have recorded ground motions from this earthquake and have plotted it. And the middle solid line is the median line. And you can see not everything is following that, because there is inherent randomness. So it's kind of a distribution around that, and you often model that, with a mean and a standard deviation. So that standard deviation is that aleatory uncertainty. And then we also have epistemic uncertainty, like I mentioned. And in ground motion models, we account for this by using multiple ground motion models. In the exercise yesterday, when you were doing the Charlevoix scenario, you had the central relationship, which is one ground motion model, and you had the high and the low. This is trying to sample the space of what are possible models for the ground motions. So on the left here is just a selection of ground motion models that are all trying to predict what the shaking would be from a magnitude 9 at about 65 kilometers. And we handle epistemic uncertainty in the form of a logic tree. And I'll talk about this a little bit more, but basically the way it happens in the probabilistic seismic hazard analysis is often when there's a choice and you don't know because there's epistemic uncertainty, you add a weight to that branch. So I believe that this ground motion model is the correct model. I'm going to give it a weight of 0.2. And another one I might give a weight of 0.3. And then you have these very large logic trees that you then evaluate. So we have models for where earthquakes occur and how often. We have models for what the ground motions are, and we have models for uncertainty. And then there's a whole bunch of math that we do to combine this into a probabilistic framework so that we can solve for the probability of shaking or for the shaking corresponding to a certain probability. And this is what I call a very oversimplified calculation of PSHA, just one part of it. So on the left scale, we have, again, a ground motion model. We have the median relation as a function of distance. And then we have probability density functions around that, which kind of reflect the aleatory. And we might ask ourselves, what is the probability of experiencing 1g of ground motion at a couple of different distances? And then what that turns out to be is just the area under the probability function, and then you sum it. And then you have the probability of having 1g or larger. And then on the right-hand scale, you would do that for every single type of earthquake, and then you would sum all of those, and at the end you would be left with a hazard curve, which is basically a graph of rates of exceedance versus ground motion. And for building code, we typically talk about 2% and 50-year hazard. That's the standard level at which we design for across Canada for building code purposes.
That is the distribution of the PGA value. So are we sure that shape?
Typically, we model them as basically kind of these log normal distribution across it. Yeah.
For those who can you repeat the question?
Oh yeah, sorry. The question are we sure that this is the shape of the distribution across of it? And I'm not sure if we're so much sure, but the data we have suggests that this is a reasonable shape for modeling this type of normal distribution across it. And so that was an example of doing it at one period, at PGA actually, and then you would do that for many different periods, and at the end of it, what you would get is a uniform hazard spectra. It's uniform because every single point along it as a function of period was calculated for the same probability. In this case, the red line is for a 2% and 50-year probability, and this is then what engineers use for design ground motions. I know that is a lot of information, so I tried to have some references on the slide as well. So afterwards, you guys can pull these up and kind of have some extra reading if you need clarification on some of the points. So at the end of it, you have these for a bunch of different points, but you can also make maps. For example, a period of 0.2 seconds at 2475 years. 2475 years is the return period. That's the same thing as saying 2% and 50. A 2% and 50 chance, it's like an event that happens once in 475 years from a statistical standpoint. And so this point right here is 0.2 second shaking for Vancouver with a probability of 2% 50. And I can do that for every single point and make a map. And so this is often what you'll see on our websites or on posters. So I'll talk a little bit about some of the components of the national hazard map. So we've been doing this for a long time, since about 1953. And the maps have really progressed from kind of qualitative assessments. So at the beginning, we basically just drew zones, or somebody drew zones, and then kind of assigned a number to it based on what they perceived the seismic hazard was in that zone, all the way from 0, which we would say no damage, to a zone 3, which we call major damage. And then we moved in 1970 and 1985 to more probabilistic assessments. And then we started adding, we used to just solve for peak ground acceleration and then peak ground velocity. And then we started introducing these spectral accelerations because that's what engineers were asking for. And so in 2020, that's the latest generation. So it's still just what we call proposed. It's not final. And it goes for public comment kind of early next year. And then it would come into force on a national level at the end of 2020. It's important to know when I talk about building codes are a provincial responsibility. So as a national body, we make national assessments, we make national building codes, and then it's up to the individual provinces to kind of legislate either all or portions thereof, but there's typically a bit of a lag. For example, British Columbia just put into force kind of the 2015 hazard model last year, so there's a bit of a lag. So in the 5th generation model, there was a lot of advancements over the 4th generation. I won't spend too much time on this, but effectively we added a probabilistic treatment of Cascadia earthquakes, which wasn't there. We kind of added more data in terms of where earthquakes are occurring. We homogenized the catalog in terms of moment magnitude, and then we had new ground motion models and foundation factors. So originally, the 5th generation model, which was used for the 2015 edition of the building code, it was developed in software we call GSC Frisk. Frisk was a commercial software, and then we made various edits, so it became called GSC Frisk. It was later then ported to OpenQuake, and generally the results matched to within a few percent, and where there is more mismatch, we generally understand why, and it's typically in areas of lower risk. And then we've worked with GEM and NRCan to kind of further reduce the mismatch and to add site amplification. So here's what the logic tree looks like for the 5th generation model in Eastern Canada. And I'm just going to step between these. So this is, again, the epistemic uncertainty, where we have alternative models. So at the first point, we have alternative models for actually where earthquakes occur. And I've kind of talked about this at length. So we have the historical model, the hybrid model, and the regional model. And if you look to the left, we have certain probabilities or weights associated with them. You know, the H2 model, the historical model, gets a weight of 0.4, the hybrid model gets a weight of 0.4, and the regional model gets a weight of 0.2. The next step, we have ground motion models. And in 2015, as we saw yesterday, we used the Atkinson and Adams relations. And these are typically what we call representative suite relationships. The authors looked at a whole suite of ground motion models and then decided to create a 3-branch representative suite. One central relation that they felt was a good description of the median, and then high and low branches to characterize some of the higher predictions and some of the lower predictions. I realize I'm showing Western Canada ground motions on this slide, but we have a similar 3-branch representation for the Eastern Canadians, basically the ground motion models you guys used yesterday for your scenarios. And you can see the weights there, 0.5 for the central branch, 0.3 for the high, and 0.2 for the low. Another thing to keep in mind is ground motion models are parameterized to different types of distance measures, and this was talked about a little bit yesterday. So for example, the Eastern Canadian and the in-slab seismicity are parameterized to a hypocentral distance, but the fault relations, like the interface relations, are parameterized to the closest distance along a fault rupture or a fault model. And this is important when you're interpreting scenario models, because for example, the NBCC 2015 ground motions, you notice that it made kind of a bullseye scenario hazard or scenario ground motion. And this is because it's only looking to see where the earthquake originated from a point, and then it's calculating it. Whereas when you do the second example, when you use the Yenye-Atkinson relation, that one asks, well, what is the closest edge to the fault? And that way you could actually see the dimensions of the fault when you did the scenario hazard model. So the next part of the logic tree is the actual occurrence rates of how often earthquakes occur. And I showed you that we have these kind of plots of cumulative rates. And I'll just remind you how you read these, is on the left scale, it's a cumulative rate. So for example, this right here, it says this is the annual rate of magnitude 6 earthquakes and larger. And then we have so this particular branch is we have 3 alternative models for what we believe is the largest magnitude possible, or what we call the maximum magnitude. And so I show those 3 alternative maximum magnitudes for the Ontario background source. So this is actually where London falls into the Ontario background source, which is why I chose this one. And here's just a map of how the kind of distribution of the central MMAX in Eastern Canada. And so this is what we believe is the largest possible earthquake. So again, along the St. Lawrence, where I showed you, we have these old rift structures. You know, we believe up to a magnitude 7.8 is possible. You have to know that these are at very, very low probabilities. So they would be very rare events.
Is that means like hybrid within the
yeah, so for Eastern Canada, for aerial sources, they're truncated Gutenberg-Richter relations. So the next part of the recurrence is we have alternative models for what the actual magnitude recurrence statistics are. And so these are the A and B values in a Gutenberg-Richter relationship. And so on the left, I show you we have a central model, an upper, and a lower. And these are trying to sample the kind of what we believe is the best estimate, and then what is perhaps a high and a low estimate to these parameters. And then you can put these 3 branches on the same plot, and then this is what it looks like. And so these are all of the possibilities of the recurrence statistics that we believe for this source. So the last part of the logic tree are depths of the earthquakes. So typically we model each source with 3 alternative hypocentral depths. So these are where the earthquakes are originating. For example, in Montreal, we have a 5, 10, and 20 kilometers, 10 kilometers being the most probable. But then in the Ontario background source, you can see we believe that earthquakes tend to be shallower, so most of the weight is at the 5 kilometers. So how we do this in OpenQuake is a bit different. So what I showed you is kind of the idealized case, and this is how it was originally implemented in software. In OpenQuake, we've collapsed a lot of these branches so that we don't actually evaluate them. And I'll show you what this means. And this was effectively done to speed up the runtime. And you can collapse it in such a way that you preserve the mean hazard. So rather than evaluating every single branch, we'll just say, well, I'm just going to collapse all of it into a single branch. And so I won't evaluate it in my logic tree, but it'll work out to the correct answer for mean values. So when you look at mean values, they still end up being valid. So here's an example of how you would do it for recurrence statistics. So you can see we have all of these 9 curves. What you can do is you can just calculate, you can effectively use the weights of each one of those and just sum them, do a weight, effectively a weighted sum of them and just come up with one. And so in this case, this kind of black dotted one is the collapsed version of these 9 relationships. And so in OpenQuake, in the model you guys have, this is what we're doing. So if you look at mean hazard, it's fine, but if you wanted to know what the 80th percentile is, it's not necessarily valid because we're not enumerating all of these branches. We're collapsing it down. For completeness, we're also not doing the depth in the same way. So in the 2015 model, we saw we had different branches for weights. But instead of, in the OpenQuake implementation, instead of having different branches for the weights, we're effectively collapsing it and just simulating earthquakes at the different depths, but not in a logic tree. I know that's confusing, and I'm happy to talk to people individually about that if they're interested. So like I said, the collapse model is okay for mean hazard, but not for other percentiles. So for example, the median value would not be consistent with the model. So when you have ground motion models, they're typically at some reference site condition. And we know that your local geology, so the soil conditions underneath your feet, have a big impact as to how strong the shaking is. If you're on bedrock, on hard rock, the shaking is typically less than if you were on soft soil or on clay. And so we try to include this in a hazard assessment by doing what we call a site amplification. And the way it worked in 2015 is you would effectively calculate hazard across Canada for site class C, which is what we call as firm ground, and then you would go to a table and you would figure out what your local site condition was, and then use this table to scale your value to determine what your hazard was at your site, whether you were at hard rock or very soft soil. In the version that you guys are running for OpenQuake, we thought that it would be, for the risk model, we actually have an assessment of what site conditions are across Canada, and so we'd like to incorporate that into the hazard model, or sorry, into the risk model itself. So rather than just calculating risk over a uniform site condition, we calculate the risk for an assessment of what the site condition is at every single site. And so in order to do that, we've had to add a site amplification term onto the ground motion models. And again, I'm happy to speak to people if they want to know more information about that. So what I haven't talked about, but is very important from a national standpoint, is I haven't really covered Western Canada. In Western Canada, we have fault sources, including this Cascadia subduction zone, which has its own logic tree. And I just have some references here for people that are interested in learning more about what the hazard model looks like in Western Canada. So in summary, for the 5th generation model, we ported it to OpenQuake. We had to do some simplification to reduce the runtime, but the simplified model is fine from a mean hazard standpoint. And we also now have a site amplification term, which means we can calculate risk for different site conditions. So are there any questions before I keep going to kind of the last piece of this? Sure, there and there next. Oh yeah. Yeah. So the question is, in some places in Canada, we have actually a lot of induced seismicity. And so the question was, how do we identify induced seismicity? And then perhaps there's another question that says, how do we handle that in the hazard model? So the seismologists, when they're looking at the earthquake kind of recordings, kind of as they happen, they make assessments. Do they believe this is an induced earthquake? So an earthquake caused by some sort of man-made process like wastewater injection. And oftentimes this is based on a proximity thing. We have a pretty good handle of regions where induced earthquakes are happening. So typically we say that any earthquake in that region is suspected to be induced. In the hazard model attempts to produce what we believe is the natural long-term seismicity or hazard. We do not consider induced seismicity. And effectively what we've done is in regions where we know there is induced seismicity, we've effectively cut it out. And so we are not solving for a hazard from induced seismicity, but only from what we believe is the natural long-term seismicity. And one of the reasons for this is because induced seismicity seems to be very variable in time. If you stop wastewater injection or move to another region, the rates might change. But the building you've already built. And so you're trying to assess its natural seismicity. There are counter arguments to this, which I accept, but that was a decision that was made when we made the 5th generation model and the 6th generation model. Another question?
I was going to ask about the fact that you said you collapsed some of the branches.
Yeah.
The tree.
Mm-hmm.
I was wondering how it affects, do you have any idea how it affects the hazard curve, which includes the hazard curve has the values for different rates?
Yeah.
So you know how it would affect it compared to 2020?
Yeah.
Higher, lower, does it affect it?
So the question is, the collapsing of the branches, does it affect the hazard curve? And the hazard curve being one of the primary outputs of a probabilistic seismic hazardness, being the probability of exceedance as a function of ground motion. The answer is the mean hazard curve should not drastically change. So the mean hazard curve, whether you do the full enumeration or the collapsed enumeration, is the same, but the 80th percentile hazard curve would not be the same. Does that make sense? We've collapsed it in such a way to preserve mean values, and that should be valid across all probabilities or exceedances. Yeah.
Is there an effort for time dependence, mostly predict and probabilistic?
Yeah.
Mostly, I guess, in the West.
Yeah, so people have looked at adding, so typically we call these time-independent models, which means we don't consider the fact if an earthquake happened yesterday to change the probability of another earthquake happening. And one of the obvious places where this might be of value is in Cascadia, where we know we get these large magnitude 9 events, every 400 or 500 or more years. And you could say that, if 2,000 years have gone by and you still haven't had it, you might say the probability of having one soon is probably much, much larger. So we don't have a time-dependent model. Some earlier work that was done by John Adams suggested that the point that we're at in the cycle, that the hazard is relatively comparable whether we do time-dependent or time-independent model. But this is something we're going to be revisiting in the 7th generation model to see whether we'd like to introduce a time-dependent component. Okay, great. So I'm just going to kind of give you a very brief overview of some of the major changes we've made in the new model. So you guys don't have that model yet, but early next year on the Geological Survey of Canada website, it'll be released in forms of OpenQuake files. And so once at the end of this, you guys are going to be wizards at OpenQuake. You'll be able to get those files and run exactly the same thing you guys are running, but with the new model. So this model is fully implemented in OpenQuake from the beginning. And we had the biggest updates were updates to the ground motion models, and some of the Western sources were updated. So I'm going to spend some time on this. And these are the kind of changes we've made in the source model. So I'll start on the left. So this is the work of Goldfinger in 2016 of a marine geology paper. And he kind of looks at paleoseismologists to estimate how often these large megathrust earthquakes occur. And his latest work and our interpretation of his latest work to us suggests that we believe there have been more of these in the last 10,000 years than we thought so previously. So we believe there might have been 4 additional ones. And so when we recalculate the recurrence statistics with these 4 extra events, it means they happen more often, so it means it pushes the hazard a little bit up, on the order of about a 10% increase in southwestern British Columbia. And there's some references here on the slide that I encourage you all to look for if you're looking for more information on any one of these pieces. The other thing that was found is there's been a recognition that there may be an active fault very close to Victoria on Vancouver Island. This is what we call the Leech River Valley, and as we go into the US, it becomes what we call the Devil's Mountain Fault System. This has now been added into the 2020 model, and this increases hazard in Victoria. Typically less than 10%, but in certain places a little bit more. It's worth saying that if this fault was, say we found this fault in Eastern Canada, it would have a much more dramatic increase on the hazard, but because in southwestern British Columbia, the hazard is already very high, the incremental increase of this active fault in a probabilistic sense isn't as much as it might be in a low hazard region. Some of the other changes is we've changed how we discretize in-slab seismicity. So this is the seismicity that's happening in that subducting slab, which is the subducting Juan de Fuca plate that's subducting underneath the North American plate. In the 2015 model, we basically modeled that as kind of a single box, effectively. But in 2015, we model it as 3 boxes that kind of decrease with depth. So we're trying to resolve the fact that this thing is increasing with depth, and the seismicity is actually different in each one of these parts. And the other big change is an update in the ground motion models, and I'll spend a little bit of time talking about that as well. Yes?
In the first case, is it always assumed that it's the entire part of the plate that's slides, or are there segments that slide at different times?
A great question. So the question is, for the megathrust Cascadia events, do we consider the fact that the whole thing might not rupture or just pieces of it might rupture? The answer is we do not. The USGS model does. They consider that it's more likely or more often you get smaller pieces of it breaking, which you can kind of see on this plot over here. This, suggesting that this lower half might rupture every 220 years. Every 320 years, it might rupture this piece. We don't include that, largely because there was a feeling that these southern segmented ruptures don't have a huge impact on the hazard in southwestern British Columbia because they are much further. So we only consider this complete rupture event, which we say is on the order of every 430 years or so.
Michael,
No.
you're getting lots of questions, but I have one as well.
Yeah.
On the 5th generation, the eastern extent of inslab seismicity
Yeah.
is quite a bit different than the 6th generation.
Yeah.
Pushes it further east.
Correct. Yeah.
And I know there's been some debate about
Yeah.
the effect of thermal heating
Yeah.
in that zone.
Yeah.
Could you share with us some of your thinking around that and the insights
Sure.
that have shifted that boundary?
Sure. So in the 5th generation model, we use this orange dashed box. And when we make an aerial source and we estimate the recurrence in it, all of the seismicity gets effectively averaged out. So at any point within this zone was the same assessment of seismicity. However, if you look at the actual number of earthquakes, you can see that certain portions of it have a little bit more or a little bit less of them. So in the 6th generation model, we've broken it up into 3 different zones, and they're at different depths to reflect that it's subducting. And they also have different recurrence statistics. So yes, this GTP East, the boundary has moved inland more, but the actual activity rate in that source was decreased. So we don't actually believe that there's as many earthquakes occurring in this one as opposed to this one. And you can just see that by visual inspection that there are not a lot of earthquakes occurring in it. So we do agree in the sense that these more down-dipped portions of it that might be hotter aren't producing as many earthquakes, or may not be possible of producing as many earthquakes, or as large. Okay, wonderful. A lot of text, and I put this in here as a reference line that you guys can all go back to. So in the 5th generation model, we use the scaled background approach of Atkinson atoms. In 2020, we're doing what people kind of regard as more the classical approach, is we look at publications, we find authors that have produced ground motion models, we assess their validity, we give it a weight, and then we add it into the hazard model. And in each one of the tectonic regions in the West, we have kind of 4 alternatives. In the East, we actually have 16 ground motion models. So you know how you guys in 2015, you saw 3? In 2020, there are 16 alternatives. So just some examples of scenario events for Vancouver. So on the left scale, it's again shaking, so the pseudospectral acceleration, and at the bottom, it's period. So a short building would care about, you know, things in this range, whereas a taller building would care about things to the right. And these 2 events are roughly appropriate for Vancouver. So an in-slab event at about 70 kilometers with a magnitude 7, or an interface megathrust event with a magnitude 9 at about 65 kilometers. And the Atkinson-Adams relations are the black lines, and the ground motion models, which we use in the 6th generation model, are these colored lines. And you can see in general, there's fairly good agreement. There's places where the new ground motion models are a little bit above, and other places where they're a little bit below. And so you can see also the difference between using kind of ground motion models as published and the difference with this representative suite approach, who kind of looked at many publications, many ground motion models, and tried to kind of predict the kind of overall range of models. Another thing that's been changed is the aleatory uncertainty. So this is the distribution of shaking around the median value for the ground motion models. A lot of information on this line. All I'd like to say is if you look at the thick black line and compare it to the dashed blue line, that's about the change we've made from the 5th to the 6th generation. And this has had a large impact on the change in hazard. Hazard is very sensitive to this number, and increasing it has increased hazard in Western Canada. So here's an example for Eastern Canada. So these green lines are the NGA East relations. So the issue, and I kind of showed this yesterday in Eastern Canada, is we're in a stable setting. We know we can have these large earthquakes, but they happen rare enough that we don't have enough recordings of them. And recordings are what drive the ground motion models. So there's a lot of uncertainty as to what the actual ground motions are from these. And the NGA East project was a decade, if not longer, project to characterize what they believe is the median shaking and the distribution around it. And those are the green lines. The black lines are the Atkinson-Adams relationships. And for the 6th generation model, we use all of them. So we've weighted them in a logic tree and we consider all of them. The overall net impact of them is roughly, at least in this example, is about a 30 to 40% increase in ground motions. And this is what's driven changes in Eastern Canada, is the inclusion of NGA East, and also the way we've done site amplification, which I have in a couple of slides. Yep. Sorry, what is the reason to introduce it or increase it? This is a good question. So the way in which we have added the aleatory uncertainty, the approach has changed. So in the 5th generation model, I encourage you to read the Atkinson-Adams paper. They talk about how they determined aleatory uncertainty from a subset of events. In the 6th generation model, because we're using published ground motion models as published, we're using the aleatory model that those authors included in their model, and those in general are larger than the one that was suggested previously by Atkinson-Adams. And some of these increases you can see kind of in the trend globally, that people, as we learn more, we think that there may be more uncertainty. So part of that is consistent with that. You're very welcome. So here's just another way of looking at the change in ground motions. So the black lines are, again, Atkinson-Adams as a representative suite. And then I made a new representative suite considering the 16 ground motion models that we're using in the new model. We don't actually run the hazard model with these, but just to kind of compare, apples to apples. And you can see, at least in this particular example, that the new central relationship for close-in distances, which have the most impact on hazard, is comparable to that high relationship previously. And so this is driving hazard up in Eastern Canada. Another thing we've done is we've changed how we're modeling ruptures and depth distributions. A lot more of the ground motion models are now parametrized to a finite distance metric like RUP or RJB. So if you redo those scenarios, you know how you had those bullseyes? It wouldn't look like that anymore. You'd be able to see the rupture geometry in the scenario hazard when you guys move to the newer model. And so we simulate for our sources a bunch of different spinning sources. For example, this is the Charlevoix source, and you can see all the different ruptures we were considering in that Charlevoix source, effectively a spinning rupture. It could be in any given orientation. However, for a lot of sources, we've just reduced this to a handful, to 2 or 3, because it doesn't have a terribly huge impact on hazard at the building code probability level. So the big other change in the new model is site amplification. So I mentioned previously in the 5th generation model, you would calculate hazard for site class C and then apply tables to scale that to any site condition. In 2020, we now calculate hazard for a whole range of site conditions and provide that directly to the practitioner as a function of VS30. So if your VS30 is 200, we kind of provide you the hazard at 200. If it's 1600, we'll provide you the hazard at 1600. And that was a lot of work. And one of the reasons why we did that is if you look at hazard versus, so this is hazard versus VS30 for Vancouver, and if we were to do it the same way we did in 2015, we would have these blue lines. And you can see there are a lot of big jumps, whereas the red line is the actual hazard you would get if you calculated for each one of those VS30 points. And again, lots of information, but the point being is we just have a much finer discretization, so we believe the results are more reliable. And I encourage you to look up some of the paper references if you would like more information, or you can ask me after the talk when we're doing examples and I could talk to you more about it on an individual basis. So again, hazard is now provided directly for user-specified VS30, and almost all ground motion models have site terms. You can ask the ground motion model, what is the shaking, from a magnitude 6 at 10 kilometers at a hard rock or at soft rock? And so we've incorporated those. And this is what it looks like for all the different relations. The black, again, a lot of information. So I have a reference there that you guys can look at. But the point being is that we're sampling a much wider range in an epistemic sense than we did last time. Similar story in Eastern Canada. One of the things that has been a big research focus in Eastern Canada is whether the site conditions here are comparable to the site conditions elsewhere in, say, Western Canada or California, because the geologies are different. And so we've made some progress towards this by including some models that are more appropriate for Eastern Canada, but there's still a lot of work that needs to be done. So at the end of it, you can get hazard as a function of ES30, which we think is a much better product that we're delivering than we did at previously. So here's an example from Vancouver and Montreal for a short period, short building, or a long period, taller building of the hazard as a function of ES30. So here is a short period map at site class C. Here's the 5th generation model, and on the right is the 6th generation model with the same color scale. The pattern of size or hazard is very similar. The colors are just deeper, which reflect that hazard in general has increased, or our estimate of hazard has increased. And then I just have some series of slides that to show kind of just examples of how much the hazard has changed in different regions in Canada for one particular measure, which is a short period at Class C. You have to keep in mind that there are almost 500 different variables that we can map. So the changes for one aren't necessarily the same as the changes at the other, but in general, the values have increased. So if you look at Southwestern British Columbia, for short period values, you can see Vancouver has increased by 36%, Victoria has increased by 53%, and this is the compounding effect of many things like adding more megathrust, adding the Leech River Fault, changing. I'll talk louder.
Yeah.
Okay, no, it's back. Okay, great. And then if we look at Eastern Canada, the changes are larger, and that's largely because the hazard is a bit smaller. So on an absolute sense, the hazard hasn't increased as much, but on a relative sense, it has increased quite large in certain places. But in a lot of these places, the hazard was kind of smaller to begin with. And you can see some examples for key cities. You can see that for these examples that I've shared with you, it's an increase of about 40, 50%. So in summary, major changes in the new model, and we believe all of these are improvements kind of in line with the global work and our global understanding of seismic hazard. It's still preliminary, it's not final. It's going to be going for public comment in January 2020, and there'll be a series of GSC open files with the model files and values that people should just be able to plug and play into their OpenQuake files to run and solve for. And then look, a lot of references for you guys to review at your leisure. Thank you. Karen?
First, regarding the inputs for the model, is it really only the files or like previous version of the bias version, just base versions? Is there another version?
That's a good question. I'm not sure we've thought that far ahead. Certainly, we are going to be delivering the OpenQuake files. I'm not sure if we'll deliver any other form of them, but they're relatively digestible. They're XML files that could be read in by other people, but that's how we are currently internally storing the files. So we don't necessarily have immediate plans to release different versions of them. And yeah, sure, yeah. Yeah, okay, that's a fair point. Yeah. So the question is, in Eastern Canada, all of the ground motion models that we have, whether we can calculate any one of them at a VS30, at the same VS30. And the answer is yes, each one of them have continuous site terms. So we evaluate any one of them at any particular VS30 that we want. And the way we do it is kind of, these images. Each ground motion model has a continuous site term. And in Eastern Canada, none of the ground motion models actually have come with published site amplifications. So we've assigned them some. And in the reference there, you can look at the exact way we've done this. Very welcome.
Thank you very much. I learned a lot.
Yeah.
My question is more related towards natural resources Canada. What is the plan regarding the risk impact that these results will have? If there is anything hazard.
Yeah.
How the current policies for financial protection, managing safety of buildings, essential facilities. How are you internally dealing on the impact that these changes will have?
So the hazard model is created as part of the building code process, and that's its primary target. So as we're building the hazard model, we're working with the engineers as they're writing the new national building code. So the new hazard model is proposed for inclusion in the 2020 edition. But in terms of larger work on assessing what the impact is of our new estimates of hazard outside of that, I'm afraid I can't speak to that very much, but I'd be happy to kind of have the conversations later on. And perhaps Marie can answer that a bit. I have another deck which shows how our estimates of seismic hazard change with time. And unfortunately, in a lot of places, the knowledge is still changing. We're still finding out stuff we didn't know, and it has quite a large impact on the actual hazard estimate. The changes this cycle are rather larger than they have been in previous cycles, but it's not unusual to have 20–30% changes from one hazard model to other, which is just a reflection of the amount of uncertainties in this. But we feel in each new iteration, we're getting closer, hopefully, to what we believe is the true estimate of hazard.
Perhaps I can just make a brief comment. So the national risk model right now is what we call kind of the 2016 baseline model that incorporates the 2015 hazard model with 2016 census data for exposure. So we're releasing that 2016 reference model as a baseline for the purpose of looking at what would be the increase in risk if we were to implement the 2020 model. Our National Seismic Hazard Assessment has been working with the seismic engineering community in Canada for over 30 years in the building code process. And so, as Michael mentioned, there is that relationship, there is that process in place to release new versions of understandings of seismic hazard. We're just at the very beginning of that curve for risk models and various end users that would be interested in the results. So we feel it's important to put the baseline out and then measure what the incremental risk is and start to establish those working relationships with the financial sector at various levels, both public, private, and other groups that would be interested in advance understanding what the implications would be for this. So the very next step, I think, is for us collectively to implement the 2020 model, hazard model, run it through to risk so that we have those results certainly early in the new year.
Okay, question?
Just one thing, the VS30 that maybe you mentioned already, but I'm not sure if I recall. Those are measured VS30 values, right?
So we don't make an assumption of what your VS30 is at your site. So when you're doing you're building a new building or whatever, it's the responsibility of the engineer or whoever the proponent is putting up the building to determine the VS30 at their site in one avenue. And then you go to our hazard calculator and you say, my site is located at such a latitude, at such a longitude, and this is the VS30, and then we provide that hazard value. So we calculate at every single site the whole range of VS30s, and the proposal in the 2020 edition of the building code is if you are using VS30, it's a measured in situ value. Sorry? That's right, yeah, but that's right, yeah. So in certain places it works really well. In certain other places it has a bit more uncertainty. But from a building code standpoint, if you use hazard as a function of VS30, there's a lot more words to this, but in effect it's because you have a measured in situ value at your site from a geotechnical investigation. So the question is, can we incorporate uncertainty into the aleatory model for uncertainty in site classification? So the aleatory model can be decomposed into a lot of different components. So the within event variability or between event variability, and there's also a portion of the sigma that can be called the site-to-site variability that tries to capture the differences in sites that may appear the same. In our model, we use what we call the total aleatory uncertainty, and a lot of that uncertainty from site characterization is kind of implicitly embedded within it. Yeah. Yeah. So we have non-linearity is in the model. Basin effects are just starting because the GMMs are just being introduced. And by basin effects, what the question is if you have a deep basin, you can amplify especially the longer periods of motion. And this is some of the work that Sherry's group is doing and trying to assess some of these things. But the ground motion models, there's not enough of them that have that term yet. The latest USGS model will be including basin terms, and it's something that we'll be visiting in the next cycle.
Too short for us. So you said for 2020 we have 500 maps, while for 2020 we have 10, right?
Kind of, yeah.
So I guess for 2020, for each frequency, we give the maps for 50 different VS values, is that right?
Let me just go to the slide so we all know what we're talking about. Thought it was there. Oh, there we go. Yeah, so in 2015, all we calculated was hazard at site class C. That was the reference condition. And then we effectively had 10 different periods that we provided for. In 2020, we will likely be providing results still for those 10 periods, but also at about 20 different VS30s and also for a handful of different probabilities. And that's why, but I don't know if these will actually on our website be 500 maps that you can click on, but they'll be on order of 500 data sets that people will be able to interrogate for values. And we might have some, thing where you put in some values and it'll make you a map on the fly or something, but I can't commit to something like that.
The thing is that I think for Vancouver, for example, have the site class map, right? Based on
Yeah.
value.
Yeah.
And let's say in regional scale, you want to assign appropriate value of hazard for each of these classes.
Yeah.
So is it like for that class, they still choose one VS value? And
So-
you use the
Yeah, so I didn't talk about this in this presentation, but we're also still going to be continuing provided hazard as a function of site class. So we will also provide the hazard map for site class A, B, C, D, and E. And there's some descriptions of how we get that. But what people have done in the past is they'll look at a site class, say site class C, and they'll calculate what they believe is a representative VS30. So for instance, in the 2015 model, the representative VS30 for site class C was 450 meters per second.
That's still going to be the same scale.
No, the representative VS30 thing has changed a bit. But we'll still provide site class C, but it's not necessarily at 450 meters per second. It's at depending. It changes depending on the period and things like that. So yeah. But you could look at the 450 meter per second map if you wanted to and say, well, that's going to be my site class C if that's what you were inclined to do. I'm not saying the National Building Code permits this, but that's what somebody could do if they were trying to compare, for example.
That's one more question.
If our organizers permit.
Okay. For the ground motion models that you use, you said we have 16 of them for 2020.
In the east, yeah.
Yes. So are these still with the rate thing that we had for 2015? For example, for each ground motion model, we give one rate. And then
yeah. So the question is, the ground motions in Eastern Canada, are we weighting them somehow? Yeah, and the answer is yes. So they're in the logic tree, and they each have an individual weight. So NGA East provides weights for them. If you look up the publication, they produced a suite. They have one model which is 13 and another model which is 17, and they provide weights for that of how likely they believe each one of those is the valid answer. And so we used those weights plus the same weights we used for AA13, but resummed to 100. Yeah, so there's 50% weight in AA13. Of that, the central model gets 0.6 or whatever it is of that 50%, and similar for NGA East. So even though I'm showing 16 on this slide, some of them have very little weight effectively. And that's why this one, which is it's looking at it from a representative standpoint, has the weights kind of embedded into it. So you can kind of tell what the actual spread of it is. Okay, well, great. Thank you, everyone. And feel free to flag me down if you have some questions, and I can help as best as I can.